The feeder conductor from the switchboard is not protected against overload by the motor overload relay. The motor overload relay is specifically designed to protect the motor and its leads from overcurrent situations arising from motor faults or overloads. However, its function does not extend to providing overload protection for the feeder conductor. The feeder fuse switch fuse must be sized to protect the feeder conductors against both overload and fault current. The feeder conductor is considered a branch circuit extending from the switchboard to the starter. According to the National Electrical Code, the branch circuit protection device, which could be a fuse or a circuit breaker, must be adequately sized to protect the conductors of the branch circuit against overcurrent. In this particular scenario, the feeder fuse switch fuse plays a crucial role. It must be sized appropriately to protect the feeder conductor based on the conductor's ampacity. The ampacity is determined by several factors, including the conductor's material, the type of insulation used, and the ambient temperature in which the conductor is installed. The fuse should be carefully selected and rated for the maximum allowable current that the conductor can safely carry on a continuous basis without the risk of overheating. Therefore, both the motor overload relay and the feeder fuse switch fuse are necessary to ensure complete and comprehensive protection of the motor leads, and the feeder conductor. The motor overload relay safeguards the motor and its leads from overload conditions that could damage the motor windings, while the feeder fuse switch fuse protects the feeder conductor from both overload and fault currents, preventing potential damage to the conductor and the surrounding electrical system. When dealing with motor circuits and feeder conductors, it is essential to understand the distinct roles of the motor overload relay and the feeder fuse switch fuse in providing complete protection. The motor overload relay is specifically designed to protect the motor and its leads from overcurrent conditions resulting from motor faults or overloads. However, it does not offer overload protection for the feeder conductor. Instead, the feeder fuse switch fuse must be carefully sized to protect the feeder conductors against both overload and fault current. This fuse acts as the primary protection device for the feeder conductor, ensuring that it can handle the maximum allowable current without overheating or sustaining damage. According to the National Electrical Code, the feeder conductor is classified as a branch circuit that extends from the switchboard to the starter. As such, the branch circuit protection device, whether it is a fuse or a circuit breaker, must be sized appropriately to protect the conductors of the branch circuit against overcurrent. In this context, the feeder fuse switch fuse plays a critical role in protecting the feeder conductor based on its ampacity. The ampacity of the conductor is determined by various factors, including the conductor material, insulation type, and ambient temperature. Therefore, the fuse must be rated for the maximum allowable current that the conductor can safely carry continuously without the risk of overheating or insulation breakdown. To achieve comprehensive protection for the motor leads, and feeder conductor, it is necessary to utilize both the motor overload relay and the feeder fuse switch fuse. The motor overload relay protects the motor and its leads from overload conditions that could potentially damage the motor windings. Simultaneously, the feeder fuse switch fuse safeguards the feeder conductor from both overload and fault currents, thereby preventing damage to the conductor and the entire electrical system. Understanding the distinct roles of these protective devices is crucial for ensuring the safe and reliable operation of motor circuits and electrical systems. When dealing with motor circuits and feeder conductors, it's important to distinguish between overloads and fault currents. An overload occurs when the motor draws more current than its rated capacity, but the current is still within a tolerable range for a short period. Fault currents, on the other hand, are much higher and occur when there's a short circuit or ground fault in the system. Overload relays are designed to protect the motor from overloads, while fuses are designed to protect the entire circuit from both overloads and fault currents. The National Electrical Code, or NEC, provides guidelines for selecting the appropriate size of fuses and overload relays for motor circuits. The NEC specifies that the fuse or circuit breaker protecting the feeder conductor must be sized to protect the conductor from overcurrent, but it also allows for some exceptions based on the motor's starting current. Motor starting current can be several times higher than the motor's running current, so the fuse or circuit breaker must be able to withstand this inrush current without tripping. The NEC provides tables and formulas for calculating the maximum allowable size of the fuse or circuit breaker based on the motor's full load current and code letter. In addition to the fuse or circuit breaker, the motor starter also includes overload relays. These relays are designed to protect the motor from overloads that could damage the motor windings. Overload relays typically have an adjustable trip setting that can be set to match the motor's full load current. When the motor current exceeds the trip setting, the overload relay will trip, disconnecting power to the motor. It's important to coordinate the fuse or circuit breaker and the overload relay to ensure that they work together to protect the motor and the feeder conductor. The fuse or circuit breaker should be sized to protect the conductor from overcurrent, while the overload relay should be sized to protect the motor from overloads. If the fuse or circuit breaker is too small, it may trip unnecessarily during motor starting. If the overload relay is set too high, it may not protect the motor from overloads. In summary, the feeder conductor from the switchboard is not protected against overload by the motor overload relay. The feeder fuse switch fuse must be sized to protect the feeder conductors against both overload and fault current. Both the motor overload relay and the feeder fuse switch fuse are necessary for complete protection of the motor leads, and feeder conductor. It's also important to consult the National Electrical Code and follow the manufacturer's recommendations when selecting and installing fuses and overload relays for motor circuits. This will help ensure the safe and reliable operation of the motor and the electrical system. When sizing fuses for motor circuits, it's crucial to consider the motor's starting characteristics. Motors draw a significantly higher current during startup than during normal operation. This inrush current can be several times the motor's full load current depending on the motor's design and the load it's driving. If the fuse is sized too tightly, it may trip during motor starting, even if there's no fault in the circuit. To accommodate the inrush current, the NEC allows for oversizing the fuse to a certain extent. The specific amount of oversizing allowed depends on the motor's code letter, which indicates its locked rotor current. The locked rotor current is the current the motor draws when it's stalled or prevented from rotating. The NEC provides tables that correlate the motor's code letter with the maximum allowable fuse size. However, it's important to note that oversizing the fuse too much can reduce its effectiveness in protecting the conductor from overloads. The fuse should be sized as closely as possible to the conductor's ampacity while still allowing for the motor's starting current. Another factor to consider when sizing fuses is the type of fuse being used. There are several types of fuses available, each with different characteristics and applications. Some common types of fuses include time delay fuses, fast-acting fuses, and current-limiting fuses. Time delay fuses are designed to withstand temporary overloads, such as motor starting currents, without tripping. Fast-acting fuses, on the other hand, are designed to trip quickly in response to short circuit or ground faults. Current-limiting fuses are designed to limit the amount of current that flows during a fault, which can help reduce damage to equipment. The choice of fuse type depends on the specific application and the level of protection required. For motor circuits, time delay fuses are often used to accommodate the motor's starting current. However, it's important to ensure that the time delay fuse is still capable of protecting the conductor from overloads. In addition to fuses, circuit breakers can also be used to protect motor circuits. Circuit breakers have similar characteristics to fuses, but they can be reset after tripping, while fuses must be replaced. Circuit breakers also have different trip curves, which describe how quickly they trip in response to different levels of overcurrent. Some circuit breakers are designed to be adjustable, allowing the trip current to be set to match the motor's full load current. This can provide more precise overload protection for the motor. When selecting circuit breakers for motor circuits, it's important to consider the motor's starting current and the circuit breaker's trip curve. The circuit breaker should be able to withstand the motor's starting current without tripping, but it should also trip quickly in response to overloads or fault currents. Coordination between the fuse or circuit breaker and the overload relay is crucial for ensuring complete protection of the motor and the feeder conductor. The fuse or circuit breaker should be sized to protect the conductor from overcurrent, while the overload relay should be sized to protect the motor from overloads. The fuse or circuit breaker should trip before the overload relay reaches its thermal limit, and the overload relay should trip before the motor windings overheat. Proper coordination can be achieved by carefully selecting the fuse or circuit breaker and the overload relay and by setting the overload relay's trip current correctly. Regular testing and maintenance of the fuses, circuit breakers, and overload relays are also important for ensuring their continued effectiveness. Fuses should be inspected periodically for signs of damage or deterioration, and circuit breakers should be tested to verify that they trip correctly. Overload relays should be calibrated regularly to ensure that they trip at the correct current level. By following these guidelines, you can ensure that motor circuits are properly protected from overloads and fault currents, and that the motor and the electrical system operate safely and reliably. It's also worth noting that the specific requirements for motor circuit protection can vary depending on the application and the local electrical codes. It's always a good idea to consult with a qualified electrician or electrical engineer to ensure that the motor circuit is properly designed and protected. They can assess the specific requirements of the application and recommend the appropriate fuses, circuit breakers, and overload relays. They can also ensure that the motor circuit complies with all applicable electrical codes and regulations. In addition to the protective devices mentioned above, there are other measures that can be taken to improve the safety and reliability of motor circuits. These include using properly sized conductors, providing adequate ventilation for the motor, and implementing regular maintenance and inspection programs. Properly sized conductors are essential for carrying the motor's current without overheating. The conductor size should be selected based on the motor's full load current and the ambient temperature. Adequate ventilation is important for preventing the motor from overheating. Motors generate heat during operation, and if the heat is not dissipated properly, it can damage the motor windings. Regular maintenance and inspection programs can help identify potential problems before they lead to failures. These programs should include inspecting the motor for signs of wear or damage, testing the insulation resistance of the motor windings, and lubricating the motor bearings. By implementing these measures, you can significantly reduce the risk of motor failures and improve the overall safety and reliability of the electrical system. The coordination of overcurrent protective devices in a motor circuit is a critical aspect of electrical safety and system reliability. The goal of coordination is to ensure that the protective devices operate in a specific sequence to isolate faults and overloads with minimal disruption to the overall system. In a motor circuit, the primary overcurrent protective devices are the feeder fuse or circuit breaker and the motor overload relay. The feeder fuse or circuit breaker is responsible for protecting the feeder conductors from overcurrents, while the motor overload relay is responsible for protecting the motor from overloads. The coordination between these devices should be such that the overload relay trips before the fuse or circuit breaker opens for overload conditions. This is because the overload relay is specifically designed to protect the motor from damage due to prolonged overloads. If the fuse or circuit breaker opens before the overload relay trips, the motor may be subjected to excessive heat and stress, which can lead to premature failure. For short circuit or ground fault conditions, the feeder fuse or circuit breaker should open quickly to limit the fault current and prevent damage to the equipment. The overload relay is not designed to protect against short circuits or ground faults, so it should not be relied upon to clear these types of faults. To achieve proper coordination, it is essential to select the appropriate fuse or circuit breaker and overload relay based on the motor's characteristics and the feeder conductor size. The fuse or circuit breaker should have a time current characteristic that is coordinated with the overload relay's trip curve. The overload relay's trip curve should be set to protect the motor from overloads without causing nuisance tripping during normal starting conditions. In addition to the fuse or circuit breaker and overload relay, other protective devices may be used in motor circuits, such as ground fault relays and surge arresters. Ground fault relays are used to detect ground faults and trip the circuit breaker to protect personnel and equipment from electrical shock. Surge arresters are used to protect the motor from voltage surges caused by lightning or switching transients. The coordination of all these protective devices should be carefully considered to ensure that the motor circuit is properly protected from all types of overcurrents and voltage surges. Regular testing and maintenance of the protective devices are also essential for ensuring their continued effectiveness. The protective devices should be tested periodically to verify that they trip correctly and that their settings are still appropriate for the motor and the feeder conductor. The testing should be performed by qualified personnel using calibrated test equipment. In summary, the coordination of overcurrent protective devices in a motor circuit is a complex process that requires careful consideration of the motor's characteristics, the feeder conductor size, and the characteristics of the protective devices. Proper coordination is essential for ensuring the safety and reliability of the motor circuit and for minimizing disruption to the overall electrical system.